So the next triangle congruence criteria that will work is angle, angle, side. Consider a pair of triangles that meet the angle, angle, side criteria. If you knew that two angles of one triangle, so in this case C and F, with E and B were equal in measure, and that we had these two segments A, B, and D, E also equal in measure, is there anything that we conclude about the fact that those two angles are equal in measure? What can we consider next about angle A and angle D? Since the two given angles are congruent in measure, BC with E and F respectively, then if we use the triangle sum theorem, we will know that A will also be congruent to D. If any two angles are congruent, we can use the triangle sum theorem to help us know that these are congruent as well. So if we focus on just the congruencies that are shown now, just AD, the angles, those two segments, and then the angles B and E, what formerly learned triangle congruence criteria can we use at this point to determine if the pair of triangles are congruent? Well, it's angle, side, angle. Here is your angle pair, here is your side pair, and here is another angle pair. Therefore, we can say that the angle, angle, side criterion is actually an extension of the angle, side, angle. It makes sense because they both include or involve two angles. The difference is whether or not the side is between the two angles, and in this case you can see that it doesn't matter if the side is between the two angles or not. You can still prove that the two triangles are congruent. Next we have one final and fifth congruence criteria, hypotenuse leg. Okay, so hypotenuse leg are names that we would call the sides of right triangles. So if we have these two right triangles, we can see that angle B is the 90-degree angle, such as B prime. And then we have that segment AB is congruent to segment A prime, B prime, while the hypotenuse is one of the congruent sides, so that AC is congruent to segment A prime, C prime. So the hypotenuse is in green. Remember, that's the side across from the 90-degree angle. And then one of the legs, it doesn't matter which one, is congruent to the corresponding leg for the other right triangle. So as usual, we can map these to each other, beginning with a ray that joins corresponding points. And we're going to get the two corresponding hypotenuse sides together by first starting with a translation. So now C prime has been mapped to point C. Then we will need to do a rotation about point C so that the A prime will map to point A. And now we can see that the hypotenuse from each of the two triangles lines up, and the points A and C line up, while we just still have the point B prime, or we could call it B triple prime if we needed to, but we do have the point B prime with that 90-degree angle there across from this line. But we're not going to be able to explicitly use a reflection across AC here either. Instead, we are going to continue our proof in the same manner that we did for side, side, side. We are going to draw an auxiliary line connecting B to B prime. Since our two orange segments are congruent, then we know that the triangle A, B, B prime, this one here highlighted in yellow, is going to be an isosceles triangle. And since it is an isosceles triangle, that means that the base angles are going to be congruent. So that is going to be this portion over here is congruent to this portion over here. Now, if you remember for the side, then we said that this right part was a isosceles triangle as well. But we don't know the lengths of BC and B prime C. We don't know if they're congruent, so we cannot state that they are isosceles at this point. But what we do know is that the full angle ABC and AB prime C both add up to 90. So that means that if I take 90 and subtract the congruent angle that's marked right here, whatever that value could be, we'll just put an X, then I have to get the value of this angle here, we'll just call it Y, no matter what it is, because they are going to be complementary. So that means that if this is X, I will also get Y down here. Therefore, these two angles are congruent because they are both complements to 90 degrees. Therefore, we can say that BC is congruent to B prime C prime. So we were able to say that those two sides were congruent because the isosceles, it became an isosceles triangle here for CB prime. If the base angles are congruent, then the sides are going to be congruent. Okay, so what do we have now? We have a pair of a new pair of sides that are congruent in addition to the two pairs that we already had. So that means that now these two triangles are congruent by side, 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 thus proving why hypotenuse leg works. Next, we are going to examine two criteria that do not prove congruence for two triangles. The first one is side, side angle. That would be if you had two pairs of corresponding congruent sides and one congruent angle, but that congruent angle is not included, meaning that congruent angle is not made by the rays of the two sides. So let's take a look at why that doesn't work. Let's begin by using this triangle here as a demonstration. So we have triangle ABC, and we know that we have the length for side AB, which is 7, and the length for side BC, which is 5, and then the measure of the angle A, which is 39 degrees. So we don't have another triangle to compare it to just yet, but we can see that we have information about two sides and then one angle that's not included with those two sides. This angle, 39 degrees, doesn't use the side with the 7 and the side with the 5 for the ray. It only uses side with the 7 to make the angle, while the other side is AC, and I don't have any information about that side length. Okay, now let's just very simply make another version of this particular triangle that keeps all of those measurements exactly the same. What I'm going to do first is I'm going to draw the ray for AC. So see how it extends all the way past, because in reality all we have is the 7, the 5, the 39. It doesn't matter how long AC is. We're trying to see if we can make a triangle that has those qualities, the 7, the 5, the 39, where the 39 is not included, but is a different triangle. So if I extend AC as a ray, can you imagine, what if we were to kick this side out? If you were to kick point C out a little bit further down the ray so that it still was 5 to point B and everything else remains unchanged. Is that possible? Haha, what do you think? What if point C, instead of being located here, was actually a little bit further down right there? So you still have a triangle with the side length of 7 and 5, just like the original blue shaded triangle, and that 39 degree angle. So we can tell that it's not always going to make a congruent triangle. Sometimes it will, but if that angle is not included between the two sides, you cannot guarantee which of these two scenarios you're looking at for your triangles. Therefore, side-side angle does not work. And the final scenario that we're going to look at is angle, angle, angle. What if we have two triangles that have three pairs of congruent angles? Here we have two triangles that are clearly not congruent to each other. Because remember, if two triangles are going to be congruent, they have to have all parts that are congruent. And so we can clearly tell that triangle DEF is bigger than triangle ABC. So the side lengths will not be congruent, so it's not going to work. But one thing that is happening here with these, let's take a look at these angle measures between what appears to be corresponding parts, because they kind of look like something else may have happened. Alright, so the angle at point A is 62 degrees. The angle at point D is also 62. So they have congruent angle pair, right? Now what about the angle at point B, as in boy? That one is 74. Then the angle at point E, also 74. Another pair of congruent angles. Interesting. Lastly, let's check the measure for angle C, 44 degrees. And then the measure of angle F, also 44 degrees. So as you can see, every single angle is congruent to another angle in the other triangle. But these are not congruent triangles. They're not the same size. The side length measures are not the same, therefore they cannot be congruent. All corresponding parts have to be congruent for the triangles to be congruent. This is a different kind of scenario that we will discuss later in geometry. We do know that if two triangles are congruent, then they do have all congruent angles. So obviously there is a chance that they could be the same size, right? But if all you know is that the angles are congruent, you are not guaranteed that the side lengths are the same. You could have a scenario much like the one pictured here.